Set. So we're going to do a quick review, and then we're going to fly like crazy on the last two big senses. And as I was just talking very briefly with Pastor about this yesterday, he immediately said, oh, that's going to work in really well with two of his sermons that are coming up very shortly. So when he's preaching about the Word, don't be thinking about the senses, okay? Just focus on what he's saying. See, I planted that deep there, huh? Okay, so last week we talked, as we were talking about the immune system, and I got the number of viruses specific. No, Mike isn't here today for me to throw numbers at him, so I got to throw them at somebody else. And I don't know whom I'm going to pick on because you guys are sitting together, so. But anyhow, the question was, with the whole fall and the viruses, what do they have to play? So there's about 30 million species of viruses, and of those 30 million, only about 200 will cause diseases in humans. So most of those viruses don't affect us negatively. They can't affect us. Okay, so get rid of that sheet. And do you remember we were talking about smell olfaction very, very briefly? So we talked about this huge nasal cavity, not huge nose, that depends on us. You know, I've got a big nose, but you've got this huge nasal cavity, and as you breathe in air with odorant particles, anytime that you smell, like pizza, fresh baked bread, we like that. Dead raccoon, we don't like that. So that stuff comes in, and it hooks onto that cribiform plate. Remember we talked about the idea of, oh, got to plug in my little guy every time I mess up, don't we? Come on, fingers. Old arthritic fingers and small things don't work so well. Okay, so as those odorant molecules come in, up here at the top of the nasal cavity at the base of the brain, remember there was that bone, that ethmoid bone, had all those little holes, and you have these special cells, supporting cells and smell cells, we can call them that, and the odorant molecules, because this is moist, they attach to that, and then those nerve fibers get up here, and you have 500 different types of olfactory cells. Do you kind of remember that? 500 different kinds. So I gave just as an example, if you order pizza and the pizza shows up and it smells really good, one particular odor, like the pepperoni, might be firing off olfactory cells number 7, 32, 59, do you follow me? And all of those different combinations give you all the different smells. Those get carried up to these olfactory bulbs, which then get carried up to the brain for interpretation. We concluded with the idea that as these nerve fibers are going up to the brain for interpretation, some of them get sent to a part of your brain called the limbic system, which has to do with memory. Do smells evoke strong emotions? Positively and negatively. How many of you have ever eaten food that you ended up with food poisoning? And anytime you smell that, what do? Yeah, you know, it doesn't leave you, right? It's a real, on the other hand, so guys especially, remember the first girl you dated and her perfume? Roger, that's because there's a 100-year memory on this stuff, and you've exceeded that, so sorry, can't help you with that. Okay, so one other term I wanted to talk, and this is really kind of funny, there's a term called synesthesia. Synesthesia, and that is where the wiring of your senses gets kind of messed up on the way to the brain. So, think about this, Aaron. Let's say you had synesthesia. So your wife bakes you a lovely pizza, And as you smell the pizza, instead of smelling the pizza, you see the color blue. Whoa, that's synesthesia. Or I might look at Roger's yellow, and instead of seeing a yellow, I might smell something because the wiring gets messed up on the way to the brain. Talk about wackiness. Maggie's not happy. She must have that condition. So that's just a really, really strange condition that occurs. Okay, so we talked about this. There's a nice picture of it. This is a video which we're not going to look at.
Welcome to 2 Minute Neuroscience.
Oh, we don't want to do this.
Neuroscience topics in 2 minutes or less. In this installment, I will discuss.
Okay, we don't want to do that. Okay, so now we're to the eye. Phenomenal little deal. So this should be figure 92 in your handout. We went color today. Pastor said below the budget, so you should see a number 92 color. And as we look at the eye, so obviously what we're doing here is we're looking at the eye from a side view. The eye has 3 layers to it. It has this outer protective layer here. The front part of it, the anterior 1/6, is called the cornea, and the posterior 5/6 is called the sclera. And have any of you ever had in your good old science days, you got to dissect an ox or cow eye? Well, you can get a really sharp scalpel, and when I would have my students do this, I would say be very careful, because to cut through that outer protective layer is a chore. Even with a sharp scalpel, you've got to get it just right and push hard to get through it. Is your eye really well protected? Collagen fibers, which make tendons, are tendons really strong? Yeah, stronger than steel pound for pound. So both the sclera and the cornea are very tough material. You could actually, don't try this at home, you could actually take a fairly sharp knife and poke the front of your eye and it won't go through.
Can you get poison?
Pardon?
Can you get poison?
No, won't get poison. But you can scratch it, but it is very hard to puncture. That's pretty cool because it's just sitting right there, but it's actually very, very tough. Now the difference between the cornea and the sclera, which is the outer protective, again, it's made up of these microscopic collagen fibers. But the collagen fibers in the front have a different twist to them, so they're transparent and light goes through them. Now think about that. How did you evolve collagen fibers with a different twist here than there? Because you know this is the white stuff, right? That's the white of the eye. So Roger 100 billion years ago, okay, if he wasn't smart enough to have evolved clear collagen fibers, he would be blind, which means he would get eaten by a predator. Do you see all of these faulty problems of evolution? So that's the outer protective. Then you have a middle, that's the red. It's called the choroid coat, and that contains blood vessels, which is really important. Hold that thought. So protective blood vessels, and then the inner retina, which is the part that does the seeing. So those are your 3 major layers. Continuing, now what we're going to do is we're focusing schematically here. Of course, you got all the stuff in the front, the outer protective, the vascular, and the inner retina. What they're doing right here is they're magnifying that section so we can look carefully at the retina. Does that look kind of busy? So this is the optic nerve leaving the back of the eye, carrying the signals up to the brain for interpretation, right? So you've got all of these different cells. You have rods, you have cones, ganglion cells, bipolar cells. You also have amacrine cells that's coming up on a different layer. So follow the light path on this. Light's going to come in through here, clear layer. It's going to hit the lens, which is a clear layer. It comes through this fluid, which is the vitreous and aqueous fluid, one in the front and one in the back. And it comes back and it hits the retina. So here comes the light and it hits the retina. And then it comes through these cells and it gets back to the rods and the cones, which actually are the cells that change light into electric signals, which go to the brain for interpretation. Now, this is what I love. I've read serious articles in serious journals saying that God could not have created human beings or the eye because the eye is improperly designed. Now follow. They say if you really want to design the eye correctly, you would have these guys sitting in the front. Because right now the light's got to go through all of these cells to get back to those. Do you follow that? But here's the issue. And I hope I don't lose you on this. Because when I get to the chemistry of actual vision, you're going to say, whoa, and I'm not going to whoa, I'm just going to keep going. But as light comes back to these rods and cones, they have to undergo a chemical configuration called conformation. And actually, every time a photon of light comes in and it hits a rod or a cone, the chemicals inside those rods and cone undergo a chemical shape change, and that takes energy. You with me? So if you're going to produce energy, do anybody remember our energy molecule? ATP. Remember we said you make probably about half to all of your body weight a day in this energy molecules. So vision takes a massive amount of energy. Is this the blood supply layer right there? Yeah. This is the protective layer, this is the blood supply layer, and this is the vision layer. Are your rods and cones right next to the blood supply? If the rods and cones were up here, how long would your vision last? About 1/10 of a second. Then it would shut down, ATP would regenerate. So you get that strobe light effect? So if we go to these experts that say God didn't design it right, what kind of vision would they have? Strobe light. Can you imagine listening to this pastor with strobe lights or anything? So, did God create it dead on? Absolutely, perfectly. Okay, is this 93?
Yes.
This is 93. So now we're going to take another peek. Here's the eye, here's our little crunch, here's that layer. So this is the stuff that is actually helping to do the vision. So we have rods and cones and ganglions and bipolars and amacrine and horizontal cells. These guys and these guys, they didn't know existed 30 years ago. So how many of each of these kinds of cells? And it's too bad Mike is not here because Mike loves numbers. So in each eye, you have to think about this, people. We throw big numbers around all the time, right? Is 1,000,000 a lot? It is a boatload. Is 1,000 a lot? So count to 1,000. How long is that going to take? Till next Christmas. But 1,000 thousands is 1,000,000, right? That's a big number. So each eye has 120 million of those. That's just in the thin layer. Each eye has 6 million cones. So the cones are for color vision, and these guys are for black and white and gray and dark light. So if you were in this room at night and you have the lights on and we all of a sudden shut the lights off, would you go blind? Yeah, you'd go blind for a few seconds. And then slowly what happens is your rod cells start picking up the very faint light that's going to filter in through the windows from the yard light. Do you follow me? But initially it'd go blind. On the other hand, you could be in this room, we could put partitions over the windows, make it totally dark in here at night, and all of a sudden turn on the lights. Will you get eye pain? Do you follow me? Because your body has the ability to go back and forth between those two. It's called sensory adaptation. And you can actually increase and decrease light sensitivity by a factor of about 100,000. And it does it really pretty quickly. You guys know what I'm talking about, right? Takes a while for you to get used to sudden dark and sudden light. So then you have these ganglion cells right here. How many rods? 120 million per eye, 6 million cones, and you've got about a million of these ganglion cells. Now, what those ganglion cells do is they actually begin to pre-process nerve signals coming in from the photoreceptors. Because remember, the light comes all the way to the back, hits the rods and cones, and then it sends the electric signals this way, and then those nerve fibers turn, and they all come and exit the back of the eye, the optic nerve. Do you catch that? So light comes in, these guys fire off, send electric signals this way, and then all those nerve fibers end up coming right out the back there, and that's the optic nerve. So on the way to send it to the brain, these ganglion cells begin to pre-process signals and send those to the brain, just kind of giving a glimpse of what's coming. Do you get that? So it's kind of like if you're looking at something, and again you have a strobe effect, you see, if somebody's running across there, you see them there and there and there and there and there. Do you follow me? And that's what the ganglion cells do to give the brain an overall sense. But by the time all of these guys are doing them, now you see a nice, smooth, continuous flow of activity. How much information is taken in? A lot. Then you have the bipolar cells, and then you have 30 different kinds of amacrine cells. And what these things do is they also process, they integrate, and they modulate. What's modulation? Modulation is kind of averaging. So, does anybody remember AM and FM? Amplitude and frequency modulation. It kind of balances things out. So these 30 different kinds of amacrine cells help to get rid of extremes so that as you're looking at things, everything is nice and smooth and not jerky. Now think about it. I was never good at basketball. I tried. Third grade, I was always the last guy. Charles Barkley always got called before I did. Okay, I was always on the bench. And finally, the way that I was wired, I was a weird little kid. You have no idea how weird I was. So I decided if I want to learn how to play basketball, I should go to the library and get a book. Quit laughing at me. I'm going to cry and go home. So I read the book twice. Did it get any better? Took something about what? Practice, right? Yeah, I'd rather read the book, so it never really helped. But anyhow, where was it going with that? I have no idea either. But anyhow, modulation. So the idea is it smooths things out. You're running down the basketball, you're doing your dribbling, correct? So you're running, and as you're running, you got all these team guys, some with you and some against you, and you're turning your head. Do you realize how much information is coming up in here? And all of that has to be averaged out so it looks nice and smooth and synchronous. So these guys and these guys actually form little clumps of mini computers right in here to send to the brain so that everything is nice and smooth. Incredible, incredible, the vision. And then the horizontal cells give you contrast. What's contrast? I don't see, okay. So contrast, no, that won't work. I don't see any, contrast. This is kind of just boring blue, right? But this is getting a little more exciting because it has what? Colors. Contrast, right? I mean, this is color, but this is different colors. So what these horizontal cells is increase your contrast so that how many shades of blue can you see? Too many. You know, in fact, I was talking earlier this morning. Guys know how many colors? Roy G. Biv. Yeah. And then these wacky women start coming up. What was color blue, Mrs. Pastor's wife? Robin blue. Who has time to sit around and think up silly stuff like that? Women do, right? You know what you can go to Sherwin-Williams or wherever. How many shades of blue? You're not going to the right store. 1,000. I mean, and all of that is because your horizontal cells give you this contrast. Pretty cool stuff? Okay. Now we're going to get to the complex. Okay. So light in the form of, make it easy.
Question, so those who are colorblind, is that the part of the eye that is off a little?
Yeah, so what happens there with most of the colorblind, and we're kind of get into that very, very tiny, but I'm glad you asked. It's an excellent question. You only have one type of rod cells, because that's black and white and shades of gray, okay? You have 3 different kinds of cone cells for the 3 primary colors. And then all of those various shades of those 3 different colors get integrated, which gives you the infinite variety of color. So if you're colorblind and you're missing one of the types of cone cells, so that whole realm is going to be wiped out. You could be missing 2. I imagine it would be possible to miss 3, but I don't think I've ever heard of anybody missing all 3. But the 3 primaries integrated give you an infinite variety of colors and shades, right? So excellent question. That's how that occurs. Okay, light in the form of photons. The smallest quantity of light. Do you remember this from physics? The smallest quantity of light is a particle known as a photon. Your rods have the ability to get activated by a single photon of light. So can they get any more sensitive? No, you can have greater acuity like eagles do, but they can't be any more sensitive. So light is absorbed by proteins found in the rods, and that protein is known as rhodopsin or visual purple. This causes that protein to change its shape, called conformation, releasing an enzyme opsin which activates transducin, which breaks down cyclical guanosine monophosphate into 5-guanosine monophosphate, which opens or closes the ion channels in the cell membrane, causing either depolarization or hyperpolarization of the cell membrane that inhibits the release of the neurotransmitter at the synapse, which means now it's not going to send a signal to the brain. This is the simple version. So when I would do this in my lecture for my students, I had about 15 steps with all the intermediary chemicals, which were huge. It was this big, ugly stuff like this. So I'd finish that slide, which was not in their notes, and their mouth is open and they're crying, and I said, you don't have to know it. In other words, this is the simple format. So to go from here down to here takes about 1/1000th of a second. How fast is that? That's pretty fast. The change of neurotransmitter, that's the chemical that gets released from one cell to stimulate the nerve cell to go to the brain. Released by the photoreceptor cells either stimulates or inhibits action potentials. So if I'm a cell and Pastor's a cell and I get fired off, I basically electrically stimulate him and he gets fired off, and it's domino effect. That's how stuff from the outside, your senses, carry information to the brain. So if I throw a ball at Ed over here and he's on his game, is he going to either catch it or move his head? Yeah, but if his neurotransmitters and action potentials are slow, it's going to hit him boom. Do you follow me? And those things, normally, if one cell's talking to another cell inside your body, those, for like when your brain says lift stuff, it's sending up to 240 messages a second to tell those muscle cells to contract more, relax, or relax entirely. So this stuff is booking. These nerve impulses travel through the optic nerve for final interpretation in the brain, and notice what happens. ATP is required for pigment regeneration. So if the retina is not sitting right next to the blood layer, if the rods and cones aren't sitting right next to the blood layer, you're going to have strobe light vision, which wouldn't be fun. Craziness. Craziness. Okay, hearing. You thought that was cool. This is really cool. Okay, 3 parts to the ear. You have the outer ear, you have the middle ear, and you have the inner ear. And everybody knows this picture, right? You've seen this before. So obviously, my wife says she doesn't like it when I get a short haircut because my dopey Dumbo ears stick out. But these are also nice. I can go parasailing anytime I want. Just get out. But the advantage is I have phenomenal hearing because these things, right? So if you're in church and somebody's telling a spicy rumor, what do? You put on the backwards ear, and now you can hear back here, right? So these babies catch sound. Then they carry them here down the auditory canal to the eardrum. The eardrum has these 3 little tiny bones called the malleus, incus, and stapes. Remember those guys? And what these things do is they turn sound waves into mechanical vibrations, but the way they're configured, Mr. Engineer, it amplifies the sound by a factor of 20. Sound so delicate to move your eardrum a billionth of an inch will precipitate sound. So, follow what happens. Sound, you catch it, gets directed down here, eardrum vibrates, causes these 3 bones to vibrate. These 3 bones sit up against this inner thing called the cochlea in the inner ear, and there's a little membrane that sits behind that called the oval window. So essentially sound is this. You catch it, you amplify it, this oval window vibrates, and that's going to cause the fluid inside here to vibrate, stimulate auditory hair cells, and when they get stimulated, that gets turned into an electrical signal which goes to the brain for interpretation. Let me hit that again. We're going to see this. Sound waves out here, mechanical amplification of these bones, oval window, the fluid inside here vibrates, and as that vibrates, it causes the membrane to vibrate, and then you've got all these little hair cells, and they bump up against that, and that turns into electric signals, which goes to the brain for interpretation of sound. Roger?
Does the cochlear implant go right straight to the bone? Is that what it does?
I can't give you the entire specifics, so I think what happens there, so you have the vestibular and cochlear nerves, that's what they have to get attached to. Now, this is the temporal bone, right? This is what's cool. You can look at some of the bones in your body and they're positive images. In other words, you have a shape to them, correct? All your bones have a shape. This whole chunk of bone right here, it has an opening inside it that is a negative image. In other words, as it forms, you don't have bone there, and it is really precise. It actually forms a snail shell. Now, it's one thing to develop a bone, correct? It's another thing to develop a bone that has missing bone in a perfect shape. Again, I could ask the evolutionist, How's that happen? They just have no idea. You get this? Okay, now follow me. Here we go. So, eardrum, malleus, incus stapes, oval window, and then you come to this. This is the balance part right here, semicircular canal, so we don't have time to get to that. But here's the cochlea. Now, what we're going to do is we're going to unwrap this snail shell, right? You're just going to uncurl it. There's a dime. There's those 3 bones. How tiny are they? Really tiny. Okay. Sound. Malleus, incus stapes, oval window, and now we took that snail shell and we uncurled it. Now what we're going to do is we're going to slice right through this. So they show you the outer, the middle, and the inner ear. You tracking with me in this so far? We good? And I'm sorry to have to go so fast. So, did we slice through the snail shell that we unrolled? Okay. Now, when we slice through, and this is the opening in the bone. This is called the Osseous Canal, and then it has membranous canals inside. So we've sliced through this. It has 3 different chambers. The upper scala vestibuli, the cochlear duct, and the lower scala tympani. Now, here's what happens. Remember our oval window, malleus, incus stapes, and that little stapes sits up and vibrates against that oval window. The oval window kind of sits up here. So when sound comes in, it causes that oval window to vibrate up and down from anywhere from 500 up to 20,000 vibrations per second. Well, this is all fluid in here. Fluid is not compressible. That's how hydraulics work, right? So you get the hydraulic, you put pressure on the hydraulic fluid, fluid can't compress, so up goes the car. Okay? So when this oval window is vibrating, this fluid vibrates, which causes this fluid to vibrate, which causes this fluid to vibrate. And then we get to this interesting little guy right here. So, as this fluid is vibrating, it causes this basilar membrane right there. That basilar membrane vibrates. As that basilar membrane vibrates, you have all of these supporting cells and hair cells. They vibrate up and down because they're attached to the basilar membrane. Sitting like a roof over the top of these hair cells is this tectoral membrane. So here's your hair cells bouncing up and down at different frequencies. As they bounce up and down, they hit this roof called the tectorial membrane. When every time they go up like that, it causes these little stereocilia to bump. And when they bump, it causes the hair cell to lose its electrical potential. That electric signal then gets carried out here in the auditory nerve to the brain for interpretation. Let me hit that again. Oval window, so they have the malleus, incus, and stapes. Those things are vibrating. Oval window vibrates. Fluid can't compress, so it vibrates. Causes this to vibrate and this to vibrate. So right in through here, there's the basilar membrane. Sitting on the basilar membrane are all of these supporting cells and hair cells, both outer and inner. On the top of your hair cells are these little hairs called stereocilia. They didn't know those existed 30 years ago. Couldn't see them, too tiny. So as these babies are vibrating up at any frequency, these hair cells here, the stereocilia, bump up against that little roof, that tectorial membrane, and when they bump, it causes the cells to lose their electric current or their electric charge, called an action potential, and it gets carried on the nerve. So these guys, once they fire off, they can regenerate their action potential. In other words, their stored electric charge. they can regenerate that electric potential in 1/2400th of a second. Do you catch that? So if I come over and I poke Pastor, his little sensory nerves, because they're sitting there with this little stored charge of 70 millivolts, which isn't very much. But as soon as I cause those to fire off, those signals will go up to his brain, and his brain will say, the pest just poked you. But those little cells, I could literally touch him again within 1/2000th of a second, and those cells have already built that energy supply back up. They've recharged, and that's how fast your nervous system works. Does that all that take energy? I know. This stuff is like I'm making this stuff up, but I'm not making this stuff up. That's how crazy it goes. So here you go. Here's those three chambers. Here's the active area. So the basilar membrane, you have the supporting cells, you have the outer and inner hair cells, and then you have these little stereocilia which bump up against the roof, that tectoral membrane. And as these guys fire off, there comes the nerve impulse to the brain for continuous sound. Okay, moms. How many of you used to listen to loud music? Okay. How tough are these things? They're so untough that we couldn't find them 30 years ago. And I can show you all sorts of electron photomicrographs of people that have been exposed to 150 decibels. And basically what it does is it makes it'll kill the stereocilia, but it'll take these outer hair cells, and when they do the photomicrographs of that, they're laying over like that. 150 decibels. Well, I'm not into that kind of music, but I've heard told some of that music gets pretty loud for a long time. That's how people can lose their hearing. Because when these guys die, they don't regenerate. Okay. Now, what you're looking at here is you're looking at, this is a scanning electron photomicrograph. What you're doing is you're looking at hair cells and supporting cells down here. And do you see these little guys up there? Those are the stereocilia. So let me give you some numbers. Oh, by the way, that little snail shell, the cochlea that we talked about way early, how big is it? It's 1/3 of an inch wide, it's 1/5 of an inch tall, and it's 1 inch long. All of this stuff in that tiny little package. Now, you like to build stuff, right? You ever built something this small with that many parts? I mean, can you even begin to imagine to build something like that? Okay, so you have 12,000, you have 12,000 per ear, 12,000 outer hair cells, 3,500 inner hair cells, and on average, each of those outer and inner hair cells have in the neighborhood of about 150 stereocilia. Mr. Math is not here to calculate that. So there's that snail shell, right? And you have the hair cells and the supporting cells, each with their stereocilia. They've removed that tectoral membrane, which would sit right above it. So as these guys are moving up and down, they bump up against that roof, and these stereocilia, every time they bump, they cause these guys to fire off, which sends the signal to your brain for interpretation. There's a photomicrograph of the supporting and the short and long hair cells, and here's the stereocilia. Now, what they found is these stereocilia just don't sit like this. They sit at an angle. Okay, and you can't quite see it. You'd have to look from the other view. So they actually sit at an angle. And the greater the vibrations, you got the long hairs that hit first, and then the short hairs that hit last. So it depends on the frequency of the sound, which hair cells, the stereocilia, are actually bumping the roof. How did this evolve? There you go. Now you can see. Do you see? Does that look like random or design, Mr. Engineer? Design. It's just there. And they'll say, no, that doesn't happen by chance. Time and chance, and there you go. Absolute perfect design. Okay, questions? Okay, I'm going to put you on the spot, Pastor. You got any concluding comments about this?
What's our theme verse?
We are fearfully and wonderfully made. So seriously now, as the pastor will be spending time, is it tonight and next week?
2 weeks.
2 weeks. And as he's talking about sight and hearing, next time you're listening to your favorite music, or moms and dads, you're listening to the little tax deductions, or you get to hear the giggles of the kids or the cries, just be thankful for all the senses that God has blessed us with. Which sense would you give up if you had to give up one of the 5? That's rhetorical. I'm not even going to entertain an answer. I don't know. I sure love good smell, but okay, so let's close. Father, we just sit and stand before you in awe just of the 5 senses, which we have not yet fully discovered the extent of, and yet you didn't even have to think about designing it, because it was in an eternity past that all of this was part of your plan. So we're humbled, we're awed. Help us, Lord, to be your children and your servants and your stewards as we take perhaps some of this information and use it as opportunities to evangelize and witness and tell others of your greatness and your goodness. We pray this in your Son's name. Amen.